Today I'll be speaking on metric reconstruction via optimal transport, and this is fairly recent work which is up on arXiv by myself and Michal Adamaszek and Florian Frick. So Florian's a postdoc at Cornell University. He's currently at MSRI this semester. Michal Adamaszek was at Copenhagen University, but now is working at the software company Mosaic. All right, so imagine we have a data set, perhaps a collection of points sampled from some shape, maybe in high dimensional Euclidean space, even though this is only drawing on the plane. Humans are pretty good in 2D and 3D at looking at these points and saying, well, perhaps these were noisy points sampled from a circle. Humans are less good at that in higher dimensions, so we want to try to teach computers to help us identify shapes from finite samples. So one way you might, well, what does a human do? A human sort of blurs their vision and thinks of these points now as being larger. And if you blur your vision the right way, you might start to see a circle here. You can make that more mathematical by defining these balls. And as you increase the radius, you get different resolutions or models of your data set. Now, in a computer, you don't want to store a union of balls. Any individual ball has an infinite number of points. And so instead, we'll store something combinatorial, a simplicial complex. So a simplicial complex has vertices, edges, and triangles, 2 simplices, tetrahedra, which are 3 simplices. And you have building blocks of all dimensions. Here, we're going to build a particular simplicial complex called the Vietoris-Rips simplicial complex. It has 2 inputs. X is a metric space, that's one input, and the second input is a scale parameter R. This is in some sense analogous to the radius of the balls. And from this metric space and the scale, we build a simplicial complex, the Rips complex of metric space X at scale R, and its vertex set is the underlying metric space, here the finite collection of points. And you add in a simplex whenever its diameter is at most R. The diameter of a simplex is just the length of its longest edge. And so we can increase the scale parameter R, and you can see how we get models of our space at different resolutions. Okay. So I want to give you some theoretical guarantees of why this Vietoris-Rips complex might be a useful tool when you're trying to reconstruct a space from a finite sample. So the first theorem that I'll say, Houseman's theorem, won't seem very applied, but then I'll describe Lotchev's theorem, which will be much more applied. So Hausmann's theorem says, if you start with the compact Riemannian manifold M, so I'm thinking of M as this double torus drawn here, or on the bottom left, I'm thinking of M as this curve. So if you start with the Riemannian manifold, which has a metric, and you have a sufficiently small scale parameter, then if you build the Vietoris-Rips simplicial complex on top of this manifold at that designated scale parameter, you recover the manifold up to homotopy type. Our prior pictures of Vietoris-Rips complexes were on top of finite point sets. Here we're doing something quite different. We're building the Rips complex on top of this infinite point set, this manifold. So on the bottom right, I've drawn a heuristic or a sketch of what the Vietoris-Rips complex of this entire manifold might be like. We certainly have edges between vertices that are R or less apart. But you actually are going to have here simplices of arbitrarily high dimension. Because if I consider any 100 points that are within distance R from each other, then I have a simplex on 100 vertices, which is a 99-dimensional simplex. So this beast on this left, this Rips complex of the manifold, is incredibly highly infinite dimensional. And nevertheless, Houseman produces a homotopy equivalence to the manifold itself. That's not yet very applied. Why would you build the Rips complex on top of an entire manifold? Lotchev makes this theorem more applied. So pretend now that you have a sufficiently dense, possibly finite sample X from your manifold. So X is some sampling of points on this manifold, this two-hole torus or this curve. So if your points are sufficiently dense, depending on the scale parameter R, then the Rips complex of this finite sample, again, gives you the homotopy type of the manifold. So it's a little bit of a manifold reconstruction. From this finite sample X, we're able to perform an operation, build this Rips complex, and recover the homotopy type of the manifold back. Any questions so far? Okay. One problem with these two theorems is that you don't know a priori how to choose this sufficiently small scale parameter R. So R sufficiently small depends on the curvature properties of the manifold. If the manifold's unknown, then so are its curvature properties. So how are you going to know if your scale parameter is sufficiently small? So one way that people try to get around this is they vary the scale parameter from small to large, and you're able to build something called persistent homology here. So you're not just computing the homology at a single scale, you're computing the homology at a range of scales. So I sort of have two examples drawn here. I have two different metric spaces on the right. I have X, which is in blue, this finite set of points. Okay. And on the left, I have the one-dimensional persistent homology barcode for this blue data set X. So as we increase the scale, we're going to recover some circle. And so in the one-dimensional homology, we'll have some long bar recovering the fact that we had a circle for a long range of scale parameters. Another example on this page is the red metric space Y. The red circle is again a metric space. You can compute its persistent homology. You'll get one long feature saying that as you vary the scale from a small value to a large value, you have a hole for a range of scales. The stability theorem says that if your input metric spaces are close in this sense, which is called the Gromov-Hausdorff distance, then the output persistent homology barcodes are also close. So X and Y are my metric spaces, and on the left I have some notion of distance between the persistent homology barcodes. And this is important in applications to data analysis because as I sample more and more points from this blue finite sample, I want my output to converge to the true output of the underlying shape, the underlying red circle. All right. So I want to speak a little bit about the proof of Hausmann's theorem. The proof of Hausmann's theorem is not as nice as one might like, and this is one thing that we'll try to tweak in our talk today. So Houseman needs to construct a homotopy equivalence from the Rips complex of the manifold to the manifold itself. Usually the way you do this is you produce maps going in both directions. Okay? Houseman is actually only going to use a map going in one direction. So he's going to consider this map from the Rips complex to the manifold, which I'll try to describe now. So a vertex in the Rips complex is just a point in your manifold. So mapping vertices of the Rips complex into the manifold is not bad. That's what the point on the left signifies. We map a vertex in the Rips complex just to the corresponding point in the manifold. Mapping an edge in the Rips complex into the manifold is also not bad. An edge connects 2 points, and the assumptions on the sufficiently small scale parameter are such that if you have 2 points in your manifold at distance at most r, then there's a unique geodesic between them. So if I have 2 vertices in my Rips complex and an edge between those vertices, then I map them to this unique geodesic between them in the manifold. So that's what this edge, blue edge in the middle, signifies. Now, when we try to map in 2-dimensional simplices and higher, Hausmann's proof gets a little ugly. So he needs to choose a total order of all the points in his manifold. And for most manifolds, there's no way to pick an order of all the points. You can sort of use the axiom of choice to get some order. But But Hausmann's map from the Rips complex to the manifold depends on that choice of a total order. So if you choose a different total order, you're going to get a different map. So Hausmann's map, I would say, is very non-canonical. So how does Haussmann map in a two-simplex? So there's an ordering on the vertices. So let's say the bottom vertex is before the top left, which is before the rightmost vertex in this two-simplex. So we have an ordering from bottom to top left to the right vertex in this particular two-simplex. The way we map in the two-simplex now is the edge between the first two vertices is the unique geodesic between them. And then we map in the rest of the two-simplex by extending paths from the geodesic path to the third vertex. So we draw all these individual paths one by one from the geodesic between the first two vertices now to the third. So in some sense, you're taking a geodesic cone over the path, the geodesic path between the first two vertices, where the apex of the cone is the third vertex. And if we had a different ordering on those three vertices, you can get a different map. And you can see now how you define Hausmann's map on a four-simplex. Now you're going to have a fourth vertex, and you cone over this bottom triangle to map in a tetrahedron. Questions about Hausmann's map? So this is a map from the Rips complex to the manifold. You might think that an obvious homotopy inverse going back from the manifold back to the Rips complex is just to include each point in the manifold to its corresponding vertex in the Rips complex. So unfortunately, this can't be a homotopy inverse because it's not even a continuous map. In a simplicial complex, the vertex set is discrete, whereas in the manifold, manifold isn't discrete. So we can't have this identity map, or this inclusion map from a continuous manifold into this discrete topology on that same set. So this is pointing out why Hausmann's proof gets a little bit difficult. He's proving that he has a homotopy equivalence without verifying the definition, right? Usually you construct two maps and you prove that the compositions are homotopy equivalent to the corresponding identity maps. So that's not how Hausmann's proof goes. He has to use a lot more machinery because he can't even construct a map going backwards. As far as I know, I certainly don't know how to write down a homotopy inverse going back, but Haussmann proves that one does exist. All right. So today we're going to talk about a different topology to put on the Vietoris-Rips simplicial complex. The simplicial complexes always have a topology that they come with. We're going to put on a different topology. And one motivation will be having a nicer proof of Hausmann's theorem with a new topology on the left-hand side. Another motivation for putting a new topology on the Vietoris-Rips simplicial complex is the following. So pretend you have a metric space, this circle, and you lose some information about this metric space. So maybe on the left-hand side of the circle, you've lost some of the points from your metric space. Okay, so you go to your neighborhood geometer and you ask your neighborhood geometer to please reconstruct this metric space for me. And so one thing they might do is they might build the Vietoris-Rips simplicial complex on top of this, your damaged version X. Okay? And there are nice hypotheses such as Lechev's theorem that say if X wasn't too damaged, then this Rips complex of X will recover the homotopy type of your original beautiful circle M. Unfortunately, we started with a metric space, and this Rips complex on the right-hand side is often not metrizable. So a topological space is metrizable if you can put a metric on it without changing the homeomorphism type, changing any of the open sets. So a simplicial complex is metrizable if and only if it is locally finite, where locally finite means that each vertex is only contained in a finite number of simplices. here, if you build a Rips complex on top of an infinite set, you'll often have a vertex that's contained in an infinite number of simplices. So we'll start with a metric space, and then we produce this Rips simplicial complex that's often not metrizable. So we sort of left the category where we want it to be. So you might get mad at your neighborhood geometer. I came in with I wanted to recover a metric space, and you're giving me back something that's not even metrizable. Like, come on, I can't even put a metric on it without changing it. All right, so that's another motivation for this new object, which I think we'll define now. So for X, a metric space, and R a scale parameter, we have the same inputs as for the Vietoris-Rips simplicial complex, but we now build what we call the Vietoris-Rips metric thickening. Okay, so notationally, the only difference is that I've added a superscript M, where M stands for metric. What I've written down here, this long inline equation, it should look familiar to you. It should look very much like the definition of a geometric realization of a simplicial complex. So on the left, I have the sum of lambda i's delta xi's. Pretend the delta xi's were just xi's. So it wasn't a delta xi, it was just an xi. All right. So if I had a sum of lambda i's xi's, that would just be a point in the geometric realization of some simplex. And the reason why is because I'm taking a convex combination. So these first two conditions, the lambda i's are all non-negative and they sum up to 1. That's saying that we're taking a convex combination of our vertices. The xi's are points in our metric space. And this condition is a condition that the simplex that we're considering, is a simplex in the Vietoris-Rips simplicial complex. Okay. So if instead of having written here this delta xi, if I had just written xi, this would be the definition of the geometric realization of the Rips complex. So what this delta xi is this is now a Dirac delta mass. So it's a probability distribution on our manifold. And as Dirac deltas usually do, this is a probability distribution that obtains mass 1 at xi and obtains mass 0 everywhere else. Okay. So each of these points in the metric Vietoris-Rips thickening is a convex combination of Dirac delta masses. So we need to put a metric on this set, and the metric that we're going to put on it is called the 1 Wasserstein metric. You can also do the p Wasserstein metrics. Let me describe the 1 Wasserstein metric. All right. So these 3 blue points, to me, that corresponds to that's a point in a metric Rips thickening. Those 3 blue points, and it's the barycenter of a triangle. The reason why it's the barycenter of a triangle is, we could have a Dirac delta mass at each of these 3 blue points, but now we take a convex combination of them, 1/3, 1/3, 1/3, and that corresponds to the barycenter of this triangle in the geometric realization. Okay, so this is blue probability measure is a point in the metric Rips thickening. The red probability measure is another point in the metric Rips thickening. It's a point in a 4-dimensional simplex, right? It's some convex combination of these 4 red vertices. So we need the notion of distance between these 2 probability distributions. And we're going to use what's called the Wasserstein distance, or the earth movers metric. So pretend we had a blue collection of dirt and a red collection of dirt. The blue collection of dirt was split into 3 piles, each of 1/3 of a pound. And the red collection of dirt was split into 4 piles, a 1/3 pound, a 1/3 pound, a 1/6 pound, and a 1/6 of a pound. And we want to find the cheapest transport plan. This is where optimal transport in the title comes in. We want to find the cheapest way to move the blue collection of dirt to the red collection of dirt. And what you're going to do is you're going to move this blue pile to this red pile, this other blue 1/3 pile to this other red 1/3 pile, and we're going to split this this final blue 1/3 pile on the right into 2 red piles, each of size 1/6. Okay, so these black lines are a transport plan or a correspondence between the two probability measures, and the cost of such a correspondence, you sum up the distance of each edge times how much mass you moved along that edge. So the cost, if all these black edges had length 1, then the cost of this particular transport plan would be 1/3 times 1 plus 1/3 times 1 plus 1/6 times 1 plus 1/6 times 1. Yeah. So the cost of this transport plan would be 1, because we've moved 1 total pound of dirt, a total of one unit distance. So in general, the Wasserstein distance between two probability measures is just the cost of the cheapest plan between them. Questions so far about the Wasserstein distance? I think here I'm trying to give you an intuitive notion. So it turns out that the metric Rips thickening is a good name because it is in fact a metric R thickening. What is an R thickening of a metric space? So Z is an R thickening of a metric space X. If Z is a metric space that contains X, the metric on X is the same as the metric on X inside of Z. So it's an extension of the metric. And the distance from any point in Z to its closest point in X is at most R. So what's most important here is that in the metric Vietoris-Rips thickening, the metric on the subset X is the same as the metric on X itself. So in the Rips thickening, if we wanted to find the distance between just 2 points in our manifold, then we'd have 2 just Dirac delta measures centered at one point on the manifold versus the other. And the cheapest transport plan, well, there's only one transport plan. You have to move all the mass from one Dirac measure to the other. And so the cost of that transport plan is just going to be the distance between those 2 points. So we haven't changed the metric on X sitting inside of the Vietoris-Rips thickening at all. In particular, the inclusion from X now into the metric Rips thickening is going to be continuous, whereas it wasn't in Houseman's case. It wasn't for the Vietoris-Rips simplicial complex. All right, great. So let's give a proof of Hausmann's theorem now for this metric Vietoris-Rips thickening. And my hope is that you'll buy that this is a simpler proof. So the statement is that if you have a Riemannian manifold and your scale parameter is sufficiently small, then the metric Rips thickening of the manifold again has the homotopy type of the manifold, now with a simpler proof. So we need a map from the metric Rips thickening to M. That's going to be called F. And this is going to send a point in the metric Rips thickening. So it's going to send this point, the sum over all I of lambda I delta xi's. It's going to send that point to its Frechet mean. So here in red, the red represents a single point in the metric thickening. And what a Frechet mean is a Frechet mean is a blue point in the manifold that minimizes the weighted sum of squared distances to all these red points. So I'm finding the best blue point that minimizes the sum of weighted squared distances to all of the red points. The weightings are just given by the masses assigned to each red point. So Frechet means don't always exist. So if you're in a circle and you take 1/2 the North Pole and 1/2 the South Pole, you can't talk about the Frechet mean of those 2 points because it could either be the left side of the circle or the right side of the circle. So once your scale gets too large, you have points that are far enough apart, you can't describe their Frechet mean in a manifold. But that's where this scale parameter R being sufficiently small comes in for us. we need R to be sufficiently small so that we can define these Frechet means. And so that now gives us a map from the metric Rips thickening to the manifold. Each red point in the metric Rips thickening goes to its Frechet mean, which is an oddness to goodness point in the manifold. So we show that this map has a homotopy inverse, which is the inclusion map from the manifold going back. So each point in the manifold maps to the corresponding Dirac delta measure. And this map is now continuous. So we have two compositions we can consider. If we start with the manifold, include it under iota, and then take the Frechet mean, that's not doing anything. So that's just the identity map on the nose. Vice versa, if we start with the metric Rips thickening, take Frechet means, and then include back into the Vietoris-Rips thickening, this map isn't the identity on the nose, but we can show that we have a homotopy equivalence to the identity. And it's sort of the simplest homotopy equivalence you could hope for. It's a linear homotopy. So T times one map plus 1 minus T times the other. Another improvement over Houseman's proof is that we do now have a canonical map from the thickening down to the manifold. It doesn't depend on the choice of total order. All right. Questions? With my student Joshua Mirth, we're looking at a version of Hausmann's theorem where it's not Riemannian manifolds, but think Euclidean submanifolds. So manifolds inside the Euclidean space with the Euclidean metric. And that works also not only with manifolds in Euclidean space, but any set of Euclidean space with positive reach. All right, so I'm very happy. In some sense, I've completed my goal for the talk already. The rest is a little bit of icing on the cake. So here's an outline of the rest of the talk. We've already sort of seen that the Rips complex and its metric thickenings might not be homeomorphic. So in settings where this simplicial complex is not locally finite, and it's not metrizable, and that means that it can't be homeomorphic to any metric space. So to see that the simplicial complex and the metric thickening aren't always homeomorphic, you just observe that the simplicial complex sometimes isn't metrizable, which means it can't be homeomorphic to any metric space, whereas the metric thickening on the right is a metric space. Okay, but furthermore, it's possible that the Rips complex, simplicial complex, and the metric thickening are not even homotopy equivalent. So in nice cases, they are homotopy equivalent, right? So when you can apply Hausmann's theorem, they're both homotopy equivalent to this common manifold, all right? But I want to show you an example where they're not homotopy equivalent, and it'll be related to the Rips complex of the circle. So the Rips simplicial complex of the circle at a certain scale parameter, as I'll try to describe, will be an infinite wedge of two spheres up to homotopy type, which is a little wild, whereas the metric Rips thickening of the circle at some scale parameter will be the three sphere. And so I gave you some motivations for metric Rips thickenings already, but this was actually our original motivation. We didn't trust this infinite wedge of two spheres. We wanted something nicer there. The final point that I'll make in the rest of the talk is that using the metric Rips thickening will allow us to say at least a little something new about Rips complexes of higher dimensional spheres at larger scale parameters. Okay, so I'm about to go off topic. I'm about to talk on the Rips complex of the circle, but this is the motivation why. I want to relate it back to the metric thickening at the end. Okay, so we're moving back from metric thickenings now to Rips simplicial complexes. And I want to describe the Rips simplicial complex of the circle. We're going to equip the circle with the geodesic, or the path length metric, and it's going to have unit circumference. So walking all the way around the circle once is is distance 1. So the way the homotopy types of the Rips complex or the circle change is that for small r, you recover the circle, as Hausmann's theorem says you must. And then at scale parameter 1/3, you get the 3-sphere. After scale parameter 2/5, you get the 5-sphere, etc. This formula up top is just describing when you have these different odd spheres, when you transition from the 1-sphere to the 3-sphere to the 5-sphere. The second part of this piecewise formula is telling you what happens at the intermediate barriers. So in between two odd spheres, you have an infinite wedge sum of even spheres of the intermediate dimension. So at scale parameter 1/3, the homotopy type is an infinite wedge sum of 2 spheres. So these transitions in homotopy types are driven by the following simplices. So when we first reach scale parameter 1/3, that's the first time we have this 2 simplex in the Rips complex of the circle. You know, this is filled in. So this is a filled in 2 simplex that destroys our circular shape. Right? So you can maybe sort of trust me that this scale parameter 1/3 is at least when the circle homotopy type should end. Who knows what should come next, but probably at 1/3, we have this triangle that fills in the circle, so the circle homotopy type should end. These other transition points come from 5, 7, 9 equally spaced points around the circle, etc. So I want to describe this transition from the circle to the 3-sphere, passing through an infinite wedge of 2 spheres. And to help build your intuition, we'll start with, not with the entire circle, but finite subsets of the circle. Okay, so here on the left, I have 6 evenly spaced points sampled from the circle. I want to consider the Rips complex at scale parameter 1/3. And the Rips complex has the homotopy type of the 2-sphere. So here's how I describe it. So the simplicial complex has 8 maximal triangles, 8 maximal 2 simplices. 6 of them look like this local triangle, 3 adjacent vertices, and all rotations of that triangle. So when you take 6 triangles and you glue adjacent ones together along an edge, and then you glue them back together to form a circle, you get this cylinder here. Right? So this is the circle. But our Rips complex also has this blue triangle in the middle and the blue triangle on the left. And so this forms an octahedron. Right? So I'm sort of gluing on a front face and then gluing on a back face. Okay, well, I'll show you the side that I was able to successfully put together. But you take this cylinder of triangles, and then you glue on a front face and a back face to get an octahedron, which is a 2-sphere. All right. So the way you should think about this is we have some simplices which up to homotopy form a circle, and then we glue on 2 disks to that circle. Okay, for 9 points, we have 9 tetrahedra that look like all 9 rotations of this tetrahedron. Together, those 9 tetrahedra glue together to form a very thick, solid torus. So it's a filled-in solid torus. And then we glue on 3 disks to the solid torus. We have not only a front face and a back face, but also this middle face. So we have 9 tetrahedra, 3 triangles. The 9 tetrahedra were a solid torus, and then we glue on these 3 disks. That's going to give us a wedge sum of 2 copies of the 2-sphere. You can see this as follows. We have the 9 tetrahedra forming a solid filled-in torus, glued in 1 disk to get a disk, glued in the 2nd disk to get a sphere, glued in a 3rd disk to get a wedge sum of 2 copies of the sphere. Okay. So that's where this 2 copies of the sphere is coming from. So you can sort of see the pattern as we go from 6 to 9 to 12 to 15 to 18 points, multiple of 3. We're going to get more and more disks that we glue in, so we're going to get more and more spheres. So This was our picture after 6 points. For 9 points, we have another disk glued in. So we have two-dimensional spheres. We go to 12 points, we have 4 disks, so we have 3 two-dimensional spheres. And then 15 points, we have 5 disks, so we have 4 two-dimensional spheres. Okay. And in the actual circle at scale parameter 1/3, so no longer are we looking at finite subsets, we're looking at the Rips complex of all the points in the circle. We have not only this one disk, but we have an uncountable number of rotations thereof. So we've glued in an uncountable number of disks. All right. And so you get an uncountable number of copies of the 2-sphere. That's where this infinite wedge of 2 spheres is coming from. Okay. Okay. So let me try to describe where the 3-sphere is coming from. So right now, at scale parameter 1/3, we have all these disks, but there's sort of open space between adjacent disks. So there's air bubbles between nearby disks. Okay. If we increase the scale parameter just a little bit, that space between nearby disks fills in. So now when we go from scale parameter 1/3 to slightly larger, you should think of there as now no longer being any space between these adjacent disks. So what we have is we have one solid torus glued to another solid torus, and it turns out that you can glue 2 solid tori together to decompose 3-dimensional space plus a point at infinity, and 3-dimensional space plus a point at infinity is a 3-dimensional sphere. So one way to think of the circle is take a line, add a point at infinity to wrap up the line to get a circle. One way you can think of the 2-sphere is you take a plane, you add a point at infinity, and that wraps up the plane to give you a 2-sphere. And one way you can think of the 3-sphere is you can take all of 3-dimensional space, add a point that wraps up 3-dimensional space to give you the 3-sphere. So in this picture, we have 2 solid tori that decompose 3 space plus a point at infinity, giving us the 3-sphere. So the first reason why we started thinking about metric thickenings is the following. Our proof of these homotopy types for the Vietoris-Rips simplicial complex is very much non-geometric. So there's no nice pictures of solid tori gluing together to give you a 3-sphere. We wanted a more geometric picture. To get a more geometric picture, we wanted these disks to not have any gaps between them, so that at scale parameter 1/3, we wouldn't have this wedge of 2 spheres, we'd have a 3-sphere on the nose. And with our new metric, at time 1/3, we do get the 3-sphere on the nose. So in our new metric, these disks are actually glued together, they're very close, whereas in the simplicial complex topology, they're not. So let me describe that a little bit. Here I have a point on this yellow disk and a point on this blue disk. So the yellow disk came from a triangle and the blue disk came from a triangle. So consider the barycenter of this yellow triangle and the barycenter of this blue triangle. So these are triangles that are nearby. So you take a yellow triangle and you rotate it just a little bit to get a blue triangle. Yeah. In the simplicial complex topology, the barycenters of those triangles aren't close. One way you could say that is you can easily find an open set that contains one barycenter but doesn't contain another. Because a set is open in a simplicial complex if its intersection with each simplex is open. So you can have this open disk in the yellow triangle that intersects no other simplex. And that open disk in the yellow triangle will be an open set in the Vietoris-Rips simplicial complex. Okay. However, in the Vietoris-Rips metric thickening, the barycenter of the yellow triangle and the barycenter of the blue triangle are close because there's an easy transport plan from 1/3 this point, 1/3 this point, 1/3 this point to 3 piles of dirt that are really close by. If you have 3 piles of dirt, each of mass 1/3 of a pound, but you only need to transport each pile of dirt an inch, that doesn't cost very much. So the distance between those barycenters are close. So in the metric Rips thickening topology, an open set around this yellow triangle, is very likely. It's certainly going to contain other nearby barycenters. So that has the effect of, in the metric Rips thickening, gluing all those disks together, even at time 1/3, to give you the 3-sphere. Whew. Questions? The nice thing about giving a slide talk is that you go quicker, right? Because your pictures are always drawn. The hard part about that is that if you need to draw something else, you can't. You need to use your hands. All right, so I have 6 minutes left, and I think this is an appropriate time to zoom through one last thing. So I'm not expecting you to understand every detail here, but I want to give you some intuition. So I want to build up to saying something new about the metric Rips thickenings of higher dimensional spheres at the first scale parameter where the homotopy type changes, right? So for a certain range of scale parameters, you recover the sphere itself. But then what's the first new homotopy type you get as you change the scale parameter? Yeah, Lori?
Henry, there's a question. So how much or by what factor does metric thickening increase computational times?
Interesting. So that's a good question. So when you're building the metric Rips thickening or the Vietoris-Rips simplicial complex on top of a finite set, those two are always homeomorphic. So the metric Rips thickening and the Vietoris-Rips simplicial complex on top of finite sets are always homeomorphic. So in applications, you have finite data sets. And so you'll get the same persistent homology for one versus the other. So the metric Rips thickening, from the sense of applications, you can safely ignore it. You might as well just compute the Rips simplicial complex, and you'll get the same topology, same homology groups. So I think the metric Rips thickening partially is useful for understanding the theory, right? As you sample more and more points, you converge to the Rips complex of the true underlying space. And metric thickenings are a nicer theoretical tool for understanding the limit, as you sample more and more finite points. There's another thing that I could say here that's a little bit more applied, which is the metric thickening, even for a finite set, it is a metric space, right? So sometimes you might want to recover not only topological properties, but also metric properties, right? And so you can build this Vietoris-Rips simplicial complex, and when the underlying set is finite, you can put a natural metric on it, and it'll be the same as the metric thickening metric. So I can understand, I can imagine applications where you don't want to recover the topology of a space, you want to recover some metric properties. And then I'm not saying that we were the first people to invent the right metric on finite Rips complexes, because on finite Rips complexes, it's pretty easy to add a metric to it. But this is just a metric that is the limit if you go from the finite case to the infinite case. So in computations, you might consider using this metric on the Vietoris-Rips thickening, but in some sense, that's the same as a natural metric that you would put on this finite Vietoris-Rips simplicial complex. Finite Vietoris-Rips simplicial complexes are metrizable.
Mm-hmm. Interesting. And what's the standard metric that you would normally put on?
Well,
finite?
I would say there is no standard metric. Well, I just said there was, but the standard metric is this metric Rips thickening. And so this metric is easy to define when the vertex set is finite or discrete, but it's hard to define otherwise. So Gromov is one of these mathematicians who's way above all of our levels, and I think it's fine to be sort of living in the shadow of Gromov a little bit, like going through and he says something true, and then you can write papers and papers proving things that he says are true. And so he has a book where he says, he uses Vietoris-Rips simplicial complexes in the setting of geometric group theory. And he says, for simplicity's sake, assume that our vertex set is finite or discrete, then there's a natural metric you can put on the Vietoris-Rips complex. And he doesn't say what that metric is because he's Gromov, but it is what the metric you would first try to write down, and it's also this metric thickening. This metric thickening is a little bit, you have to be careful to define this metric thickening when the underlying set is not discrete or not finite. So we sort of knew how everything should work before we had the final proof that we actually had a metric. We needed some fancy facts about Wasserstein metrics. Usually when people define Wasserstein metrics, they only define it on compact metric spaces. But we wanted to be able to talk about Vietoris-Rips thickenings of non-compact spaces. So we found a reference that allowed us to define the Wasserstein metric even on top of probability measures in non-compact metric spaces. Yeah. So in some sense, we're sort of doing what Gromov said we should do, and in another sense, we're actually making a new definition in the infinite case where previously no definition existed. Yeah.
Right. Okay, great.
Yeah, but the short answer to the question is in computations, you're going to be in this finite setting, and essentially it doesn't matter whether you use the simplicial complex or the metric thickening. So people won't be writing software packages for metric thickenings. You might as well just use this software package that you already have for simplicial complexes. All right, so I'm out of time, so let me wrap up by saying that the ideas that we use in the case of the circle to see the three-sphere, you can replicate in higher dimensional spheres, and we can write down what the homotopy types of Rips complex thickenings of higher dimensional spheres are at the first scale parameter where the homotopy type changes. So this is in the paper up on arXiv. To conclude, I think it'd be fun to try to learn what you can say about Rips complexes or intrinsic check complexes of spheres at larger scale parameters. Essentially nothing is known. What can you say about other manifolds? So what's the metric thickening of the flat torus at higher scale parameters? And Houseman has a conjecture in his paper about Vietoris-Rips complexes that if you take a manifold, build the Vietoris-Rips complex, then the homotopy connectivity, the level of which beneath all homotopy groups vanish, that's a non-decreasing function of R. So we saw this in the case of the circle. As the scale parameter increased, the homotopy groups at higher and higher levels vanished. Right? So first, the fundamental group wasn't trivial, but as we increased the scale parameter, the fundamental group became trivial. So did pi 2, pi 3, pi 4, etc. So is that true for Vietoris-Rips complexes? That's unknown. It's also unknown if it's true for metric thickenings. And with that, let me thank you for your attention.
Great. Are there questions for Henry?
Nice talk, Henry.
Yeah, great.
Thank you.
Okay, let's thank him again.
All right, thank you.
Oh, wait. Oh, I think we have a question. Oh, thanks again, Henry. Yeah, great.
Yes. Let me end this recording.